they'll succeed. That's a good start. And here we go. So this is an animation tool that I've been working on for procedural animation in games. And it's kind of a hardwired system, so it's not at all as cool as Blender, but it has some really nice features to it. So we have this little character here, and he is fully IK, so you can drag an arm, for instance, and play around with him. But what's really cool is that you can do sort of behaviors that are connected together. Because normally when you do animation, you want to do an animation that is a fixed animation that you run once in a film. But in a game, you want to have something really dynamic. So I'm going to take this object, which could be whatever. Let's say it's a gun. And I'm going to place it here at the shoulder, like this. And I'm going to direct it in this direction. And I can say what the up vector is. No, I can't because it's broken. And then I'm going to take this hand and put it on this gun, and take the other hand, put it on the gun, like that. Now, if I move the gun, you can see he's fully animated. And this can now be connected to, for instance, the direction the player is looking. So at the same time, the guy could be walking. So now we have a walking character that is aiming around. So this is kind of animated procedurally without having to build a specific animation clip for whatever motion. So you can sort of blend together stuff. And that's pretty cool. So let's stop this guy for a second. And let's take down his hands and remove this object. So for instance, a good example is you might have an object in a world, like for instance this box here. So let's say we want to have a character grabbing a box, right? So I'm going to take this hand, put it on the box. I'm going to put it at the edge of the box. And then I'm going to take the other hand, put it on the box. Oops, I got inside the box. And what's cool now is, of course, that I can move the box and he will reach for the box. I can even take the direction he's looking and place that on the box. So now he's kind of looking at what the hell he's doing, right? So this could easily be animated. And of course, the character might be handling a very large box, so he could just handle that. And the nice thing is once you built this animation information, it just works disregarding of the size of the box he's manipulating. So it's really easy to sort of reuse the same animation. And not just for this character, because you can actually show the setup of this character. Whoops. So here is... Here we go. Now I can, for instance, change his arms to make them longer, shorter. When he got shorter arms, he needs to reach, right? I can make the legs longer, so now he has to reach down or reach up, right? And of course, this all works when he's moving. So now we have he's walking kind of a circle just as a way of testing the walking. And he's trying to hold on to this object. So this is a pretty simple but cool way of showcasing kind of what this system is about. Now I've obviously ruined this character a little bit because his arms are weird. But let's say we want to do some animation. Now, I want to animate this guy saying hello. So I'm going to just put his arms somewhere reasonable. It's got very long arms at the moment, but what the hell. Okay, so to do that, I'm going to start an animation clip. So now we have a clip, and here's a timeline. So I could start keyframing this, but keyframing is really boring. So I'd like to do something else. I'd like to use motion capture, except I don't have a motion capture rig. So I'm just going to press record, and I'm going to grab the hand and say hello, and put it back like that. So now I created a little bit of motion capture. These are all the cutscenes, right? And you can actually change the speed of it, and you can see all these little key points, right? You can actually go in and edit them like this, right? Dragging them directly, so you don't have to go to it. Actually, with the middle mouse button, which gives you this, you can go to the next key, so you can key through it or go to the previous key. So it's a nice way of doing it, and now I can sort of move it here. You can see there's lines here. That shows you the speed of the motion, right? So, for instance, if I go to some good point, let's say this one. No, let's take that one. Okay, so here you can see, if you zoom in a little bit, you can see I'm moving very slow, this part, and very fast here. Now I can just go to this point, and if I move this on the timeline, you can see the lines change, right? So even if you make a change in the timeline, you can see it directly on the model. That's kind of useful as well. So now I can sort of stretch it out or make him a little bit slower when he's moving down his arm, like that, maybe. And then, you know, I can try it out. So what's cool about this, if we go back to the original, at any time I can actually trigger this. So I can trigger hello. And I pre-prepared some stuff, some broken stuff, I think. Let's see what we have. Okay, let's actually do another one. So I'm gonna grab his crouch, which is like, yeah. And I want him to duck down. So I'm going to record that. I'm going to say duck down and get up. So that's a movement now. So you can see that's my little animation. And now I can, whoops, I can delete this. There we go. Now I can actually go to my default and I can press, I can press the play button to do that. But the cool thing is, of course, I can do both of them. So I can do, you know, he can wave, and then in the middle of the wave, he can duck down. So different parts of the animation can trigger different parts of the character. And that's obviously really useful for when you have an animation system that's driven by a player that is like crazy and doing different things all the time. You can't really, you know, stop the player. If the player presses a button that makes him wave, and then all of a sudden it starts moving, or, you know. So that's why, you know, you can start walking. He has a really silly walk since he has so short legs. But if you now duck him down, he'll actually duck down while walking. So you can see how those are kind of, yeah. So this is kind of an experimental project that I've been working on. And, oh, there's one more thing I'd like to show you on this. I prepared this earlier. So this, now I'm using this box that we had again, and I've animated this hand we have here, and it's moving into the box and back. So this could be like pressing a button, right? Now you can see in the, oh, let's see if I can fix this. You can see there's little green lines here. Let's see if I can grab them both. There we go. So now you can see that it's easing in here to this keyframe, and it's easing out to that keyframe, and I can actually ease out a little bit more, ease in a little bit more. So now, when I go to my default pose, it will actually move from wherever it is. It doesn't have a starting point. It will just ease in to the animation, and the animation doesn't start at 0. It starts further in. So it gives you that sort of, do whatever you're doing, but start going towards this keyframe. So that means if I now press play, you can see he's moving to the first keyframe, press the button, and then go back. And of course, I can make the button smaller and have him press the button, or I can move the button over here, and he'll, you know, still press the button. And let's make him a little bit faster, because he's like super fast or something. Like, so now he knows how to press the button. And of course, I can rotate the button because it's in the ceiling now. So let's put it like that. Let's put that. There we go. So now he's going to press the button from underneath, right? So this obviously means that you can have a character running around in a game shooting, getting to an elevator, and pushing the button. And he doesn't have to line up with the button and stand in the exact right position in order to push the button. He can, in fact, use his other hand to shoot a gun or wave at somebody or, you know, do something else. So that's kind of the animation system I've been working on. And maybe there's some useful interface stuff here for Blender. I don't know. But I definitely like having the animation curves be in the 3D space so you can just move them. And the thing about having the lines so you can see the time going by in it are also really, really nice. So that's kind of that. So I'm going to quit this. See, nobody's kicking me out yet, right? They're gonna. So let's see what we have running in the background. Oh, we have a verse server. Oh, let's see. So here, I'm going to show you my modeling tool quickly. And unfortunately, I managed to lose some source code. Well, I didn't lose it, I just didn't bring it. Where the hell? Oh, there we go. So I'm going to start by starting my modeling tool. For people who don't know, this is open source modeling tool called Locaro, which is pretty awesome. So here's all the geometry, and it's using verse if you went to the verse session. So if I, for instance, start another copy of this application and connect to the same server and then see the same object, if I select some part and start changing, they're connected. So this is pretty standard verse stuff. This modeling tool, I'll see if I have any time to show it, but I've actually written a new tool because I used to, like 4 years ago, I showed a UV mapping tool here where you were able to sort of unfold things in a really neat way. And I started thinking about writing a new version because it was really cool, but it was buggy. But then I started thinking, why do you need the user? I felt that the user was kind of the problem because UV mapping is really boring. So this is my new UV mapper, and it's on this machine. It's now running in 250 frames per second, and for each frame, it's actually modifying and creating this UV map on the fly. So this is a 100% automatic UV mapper. If you don't believe me, I can just start editing this object, and you can see it automatically creates the perfect UV mapping for the object. So it's pretty neat. And let's check some other objects out. This gun, for instance. Let's see if I can find that in the modeling tool. Here we go. Yeah. So now I can change the UV of it. And it just happens. And of course, if you really want to have fun, you should go into the options of this, and in the settings you'll find animated. Ooh. So that gives you a little idea what's going on. This version is old, so it doesn't actually export back to verse, which my new version does, and it has a nicer interface where you can actually select objects and things like that. But this obviously is pretty nice in terms of performance. So now you can set the spacing, because you get bleeds when you have parts that are too close to each other, so you can set spacing if you want. You can turn on symmetry, which if you find symmetrical parts, it will do symmetric UV mapping. That can be useful if you want to. Otherwise, it will make every pixel unique, so that's really good for baking and things like that where you want unique textures. So yeah. I'm afraid it doesn't have very much interface to demo, because it's like it does it for you. So that's kind of a cool tool. Oh yeah, I'm sort of doing a preview of what I'm going to show later on. So this is something I written a game called Love, and if you go to my website, you can download pretty much all this source code, lots of source code, and also a lot of the tools. So when doing Love, I had a lot of performance things because it's a very massive game, and there's a lot of if something in the game, everything in the game is running all the time, all the physics, all the graphics, everything's running all the time. So if there's a problem with any system, everything goes slow. In a 3D application, you can have a function that is slow, but only when you run the function is the application slow. So I wrote this application, and this is a library that allows you to put points in your code that basically say, time from here to here and tell me how long it takes. And then do that for every frame, and then you can get this kind of data out. So then you can load that data into this mining tool, and here we can see, I can show you, guess that's the problem right there, right? Here you can see something's going on, right? Something's spiking up and taking a lot of performance. And they're sort of color divided, so you have all the yellow stuff is all the OpenGL stuff, and then the red stuff is real small, so we don't really care about that. That's the entities. And then we have, I think here's the entity progress, and here's the service. And the service is divided into things, so we can definitely see its geometry is really what's spiking up here, so we probably need to take a look at that code. I have to quit now, yeah.
Continue with the next session.
I'll show more till this evening at the,
The auto podium, he will.
yeah, I'll do some. Cool.
Thanks for filling in.
Yeah, you're welcome.
I've been running up and down for cables.
Okay, so let's continue with the next session. Gilberto with the MORSE simulation platform based on Blender. So please, Gilberto.
Second. I think I need just a second to reconfigure this. Yes, it normally doesn't work very well.
Was it cool? I mean, you have to extending.
So there it's displaying. But if I yeah, well, I'll have to do something like this. And yeah. Okay. Well, I'll have to do the presentation like this. So, hello, I'm Gilberto Echeverria. I'm originally from Mexico. At the moment, I'm working in France, at Toulouse, in this Laboratoire d'Analyse et Architecture des Systèmes. That's a laboratory where they do lots of different technologies, but I'm in particular working in the robotics laboratory, and we are developing this project called MORSE. It's a robotics simulator which is completely built on top of Blender. So first, I'm going to explain a bit about what's the subject of this speech. What is robotics? So robotics is, we all have an idea of what a robot is, mostly something that we have learned from science fiction, but robots in real life are kind of different. So we have to think of what the real robots are about. So they are a collection of lots of different technologies, both in software, control, hardware, all of it mixed together to try and solve a complex problem. And there's always, these problems can have different conditions, so that it's not always going to be the same problem. If it were always the same problem, that would be called automation. Doing something automatically means just reading data from a certain source, and according to that data, you're going to react to do something. But that's not robotics. That's not being autonomous. We want to have a robot which is autonomous. That is, that it can solve any kind of problem, well, within a certain range, but it can take its own decisions. It can reason about the data it's gathering and act accordingly. And there's robots which can be seen in many different applications. So from space exploration to household robots which can help you with your daily tasks. Transports, anything that moves could be automated and thus become a robot. But developing robotics is really very hard work. So there's so many things involved that we need a means to simplify testing, and that's where simulators come in. A simulator allows us better control over the environment, and we can test using under conditions that would otherwise be impossible. One of them, which is very important to us, is, for instance, testing how would a group of robots behave. If we don't have several robots, we cannot do this kind of testing, so simulator is the only way to do it. And something important I want to comment about simulation is that it can be done at various different levels. You can simulate just a particular sensor with high precision, so you can do a completely realistic simulation of one particular element of the robot, and there's lots of simulators like this. But what we at last are interested in is a system simulation of the robot, that is a simulator which presents the robot in a whole environment where it has to use all of its resources, so all of its sensors, all of its capabilities to perform the task. And now, well, this is the outline of the talk. I will first explain what's the requirements of this new simulator we want to develop, and then later talk about how it's been done. So first, a few words about the robotics department at LAS, at our laboratory. We do not create any hardware for the robots. It's all about the software that drives them. So all the control systems, all the data processing, the decision, that's what's being developed in the lab. We have many kinds of projects, in particular the ones which will be using this simulation are projects which with either teams of robots performing a common task, and this is generally done outdoors. And the other big area of research is human-robot interaction, where we want to have robots that can aid persons in their daily life. These are the actual robots that are used in the lab. The one in the center is used for the first kind of projects, outdoor exploration. So it's an automated rover robot with lots of sensors. The two robots on the sides are human interaction robots. They have arms, they can take objects and interact with a human. And now, the simulation using Blender. How was it born? Well, there's a PhD student who had this idea of using, well, Blender has always been used to model the robots, but to actually use Blender and its game engine to do the simulation. There's many features in Blender that allow us to do this kind of thing, especially because in a way, simulation is very similar to a game, only it's not a human who's going to be playing, it's the robot who is going to be playing the game. And, well, besides, we have, of course, within the game engine, the physics simulation and very good graphics. And that's very important because, as you can see, all of these robots have cameras. Most of them, well, they have stereo cameras, which are very used to navigate or to identify the general surroundings of the robot. So if we're going to do simulation, we are very interested in creating also realistic images which can be processed the same way as a real image. And of course, the most important aspect of Blender and its game engine is the ability to use Python scripts that allows us to extend and do a lot more than would be normally possible with Blender. So that was our first demo of what could be done with Blender using some simulation. So once it was proved that it was possible to do so, we had to decide why do we need a new simulator since there's already so many in robotics, and what do we expect from this new simulator. And so this is the list of requirements that were made. So we want to use Blender not only because of its capabilities, but also because it's open source. And all of the software used in the laboratory is open source, so we had to try to keep up with that. Then there's lots of different departments, groups in the lab, lots of people working with several different aspects of robotics, and we want this simulator to be usable by everyone in the lab and also by people in other labs. And that's why we want this simulator to be modular and very flexible so that you can basically adapt it to what you need. The software in the loop philosophy is a little bit of what I said. It's going to be the robot who plays the game. So that means the same software that drives the robot that runs inside of the physical device has to be connected to the simulator and use the simulated cameras and sensors instead of the real ones. But it doesn't have to be modified in any way. We have to take the exact same software and connect it using the same means we would use to connect it to a robot. And of course, then it is up to the simulator to generate the same output and entirely represent a real robot. We also want to do multi-robot simulation, as I mentioned, and the different levels of realism, also because there's people working at different abstraction levels within the robots. We may want to test the navigation of the robot, which is using the data gathered by sensors, try to locate a path for it to move, or we may want to test a higher level task where we are only going to tell the robot, go to this place, and it should be able to get there without having to rely on all of the lower level systems. So we want to create that effect that we can control what part of the control structure of the robot do we want to test. Now I'm going to talk a bit more about the component architecture. This is an important aspect because we want to create a library of individual components that can be used by any researcher. They can pick the components they want, put them into the robot, and then test individually. That's all the sensors, all the different robot platforms, control systems, and we have these two other kind of modules we call middlewares and modifiers. This I will explain a bit later. And something important is that for every component we have, there is a Blender file and a Python file. They are independent, but yet they are connected. We always keep a reference of what the code in Python belongs to which Blender component and the other way around. This is just a simple scheme of some of the classes we have. All of these are classes implemented in Python, representing each one of the components. We have a particular class for each kind of robot, for each cameras, and so on, for each sensor. They all perform only their appointed task, so they are very simple, the bare bones of what this component needs to do, and then they interact with the others to create the whole functionality of the robot. Now, besides those components which are very naturally related to a robot, we have these additional components. One is the middlewares, which is a layer of communication used to share data between robots and between different platforms. Normally, in robotics, there's always two different kinds of processors, two different kinds of architecture in a robot, so we have to be able to communicate between them, and that's the task of middlewares. They encapsulate data and share it so that it can be understood by all parts of this architecture. We, of course, have to comply with this. We have to be able to read data from middlewares, but we don't want to just code one middleware into our components. We want to be able to change that so that any lab can use our simulator just by switching what kind of middleware they want to use. And so we made all of our components unable to use middlewares, and then we have to add this particular middleware module that will kind of teach our sensors how to communicate. The other kind of modules we have is modifiers. This is important for the realism in a simulation because, well, we are simulating sensors which will gather data within the simulated Blender environment. But they always get perfect data. We can always know the exact position of every object in Blender, the exact distances, but in real world we don't have that much precision. If we have a GPS, it will always be noisy, it will be distorted in some way, or it may use different kinds of units, a different reference from that which is used in Blender. So we have to transform all of the data. We always need to correct so that we get the data exactly the same way as a real sensor would give it to us. And so this is the general flow of data within our simulation, where we have all of our sensors and their related components. I will explain what a sensor would do is each one of our sensors is going to perform its action, that's to gather data, and that to do that they generally need to consult with the simulated world. After that, it stores the data and it will loop through all of the modifiers associated with this component to gradually change the data until we have the final version that we want to export, and we do that using the middleware. This will connect to the robot software that's going to expect some sort of data, and then the whole processing and decision is done outside of Blender using the robot software. And then the loop closes when we get data back through our actuators. That's the motors that drive the robot or that make it do a certain action. The flow of data in this case is the same, only it's reversed. We first read the data using middlewares, filter it with the inverse of the modifiers, and then apply that data, generally in the form of a motion for the robot, to the Blender world. And this is a diagram of how it all integrates together. We would have a Blender and the MORSE simulator running. It can even be in a separate computer from the robot software. We will have our simulated environment, our simulated robots, each one composed of sensors and actuators. It will use the middlewares to communicate with the robot software, which will then send commands back, and it can also communicate with the other robots. This communication is handled outside of Blender, but using some information gathered from it. And so those are the requirements that we have to comply with in the development of MORSE. Now I will tell you what has been done already. It's still a work in process. And well, what do we have now, and how have we implemented all of this? So right now we have the models of a number of robots, the ones we use for these projects. This is Dalla. It's basically a representation of the first robot I showed you before. We have also the Jido robot, that's the mobile platform with a robotic arm, and a helicopter robot. These are the modules. They don't have any other components. We store all of the other components, all of the sensors, as a library, and then we can add them to these robots. Just noting that all of these robots will use the Blender Python API to interact with the world and gather the data. So for instance, we are using the biotexture module to simulate cameras. This will capture the render of one of the Blender camera objects and store it as an image file, which we can draw on top of another object or use the raw data to send through the middlewares. And so when we
each different sensor will do different things, but they all rely on the Python API to gather the data. And this is meant to be a video. Okay. This is a video of how we build a robot from our library of components. We start from a blank Blender scene, and we start linking in all the different components that we have in other files. This permits us to have each component stored separately and always updated independently of the whole robot. Then we just add them. Each component can have, normally we use an empty object to hold all the scripts related to each sensor, and one or more meshes to give the shape, and if needed, some other components that may be used for the component to do its job. Just like in real-life robots, it's very important to note the position of a sensor with respect to the robot. For instance, if you have a GPS on board of your robot, it will give you always the location of the GPS sensor, not of the robot. You have to know where is the sensor with respect to the robot so that you can do a conversion and then guess the position of the robot. If we want a realistic simulator, we have to do the same. And so in our simulated model, we have to use the same position, relative position. The same goes for all of the other sensors. Here we are adding this sensor is a laser rangefinder, which will sweep around 180 degrees in front of the robot to try to locate any objects in front. That's why we use this semicircle. And well, we can also duplicate sensors. In this case, you duplicate a camera that will immediately give us stereo vision. All of these components will have to be parented to the robot. That way, they all behave similarly, and also we will take that into account to know which sensors are equipped on board of which robot. Now, all of our sensors use Python scripts. We have chosen to store all of the scripts outside of the Blender files because we had some trouble with the version control systems. It's better for us to keep the code separately. Also gives us a bit more flexibility. And we avoided certain problems with Blender. In the case, we always have a very clear link between each Blender file and the Python file it's going to import. This is a view. I will explain about this. This is a general view of how we have configured MORSE. At the moment, we're still using Blender 2.49. We have a few Python scripts which are related to each individual scene, and in particular that configure the elements that are included inside of each scene. This is to link, well, say, specify what component is going to use which middleware or which modifier. And then we have the logic part of each component.
It's generally going to be the same. In most cases, it's going to be exactly as this one, where all of our components are going to just be constantly calling a generic Python function, but this function is going to ensure that it dynamically calls the Python method that corresponds to the object that's generating the event. And we do that by specifying these properties for all of our components. So we have, for instance, this corresponds to a robot, and so we say it's a robot tag. Otherwise, it could have a component tag, a sensor tag, or actuator tag. Then we say which is the Python class that's related to this object, and the path to the file, to the Python file that contains all of this code. This information is later used to dynamically, once the game engine has been launched, dynamically load all of these modules, and that allows us a lot more control because we can know exactly what sensors are loaded in the scene, and we can manage how they share data with other components, with the outside world using middlewares, and we can also have control when we exit the simulation, we can destroy all of these objects and cleanly close all connections. Now I'm going to show you a demo of the simulator working. It's going to be communicating with an external client outside of Blender, which we run in a terminal, but will communicate with Blender using some sort of middleware. This blue square will show the view from the camera mounted on top of the robot. And you'll also be able to see how this laser rangefinder will draw a semicircle over the area which is visible by the robot. So we have the view from the camera of the robot here. Unfortunately, as we draw as well the input from the laser rangefinder sensor, it's also captured by the camera, but we can switch this on or off. And then we have a very simple client in this case, which sends speed commands to the robot and destination commands. The robot will try to move around to reach the destination specified. In this case, there's physics enabled, but in this particular video, there was not many collisions. Now I'll show another video where we have a team of 3 robots. Again, we have the terminal from which we're sending commands to the robots and the view from the cameras of the robots. This time, this is not shown inside of Blender. This is another application external, which is receiving the image data and then displaying it. Again, this is still just a very simple client. I'm not showing the real robot software because, well, in that case you will not see much. It's just a bunch of debugging messages. Yes. So in this example, we're instructing the first robot to go to a series of waypoints indicated by the red circle. Then the other two robots are instructed to follow the previous robot. So robot number 2 will follow 1, number 3 follows 2, and you can see the view from each one of them. Each time robot number 1 reaches a destination, it will send an acknowledgement saying, I've reached this point. It then receives the next point to go to. And it's all using, in this case, the physics to follow the configuration of the terrain. And well, that's more or less what we have at the moment. There's some other things, but they're still very experimental. There's still a lot more to do. We're struggling to advance a bit. Many things, well, we have run into many problems while using Blender, as well as many advantages. Of course, using Blender has allowed us to progress really fast, but we are kind of limited. Well, it's more or less the same thing that has been said before about how especially the Python API does not allow us full control of the environment or full access to all of the data. And there's been also many changes for the new 2.5 version, which we haven't been able to integrate. We're still struggling a bit with it, but we're almost ready to do the switch, and that's going to be very useful as well, because that will allow us also to use many new features, in particular the IK solver, which can be used for the human-robot interaction. We've been working on a way of simulating a human inside of the simulator that will be able to interact with the virtual robots. So this human should be able to reach out to an object, grab it, and give it to the robot, or the other way around. The robot should be able to make an object accessible to the man. And that's something we're working on it at the moment, but still not quite ready. Well, another feature that we can benefit from in 2.5 is the configurable interfaces. We've seen a project where they give a whole panel specific to a certain application to the users. We can do that. And we are also thinking of expanding the simulator so that it can run on several computers at once, using each one of them running Blender, and sharing information to synchronize all of the events in all of these simulators, so that will lower the load on a single computer and allow us to simulate more robots working together in a team environment. And I think that's generally it. Just a summary of what we have. We're using the game engine and all of its features to create a very usable simulation using graphics, physics, and the whole dynamic nature of Python that allows us to load modules and store each component as modules, which are later loaded once we run the simulation. And that allows us for a lot more flexibility and to allow the simulator to be used in different applications within the same lab or in different laboratories as well. Yes, that's it. Thank you. The MORSE project is developed as open source as well. We are open to collaborations. If you are interested in seeing the code, you can download all of it from our website. There's also documentation. Also, documentation is a bit lacking at the moment.
Hi, I wonder, can you comment on computer vision and
Yes.
how that's integrated with the system?
Uh-huh.
Do you use OpenCV, for example?
No, no. All of the vision treatment is done outside of Blender, and it's done using the software that already exists at last. So the only thing that Blender does is capture an image and send it outside. And then, well, there's a lot of research that's been done, and image processing, stereo vision, but all of it is done outside, and then we only get instructions based on that information.
Sorry, I missed the beginning. So, did you get into contact with the robotics mailing list on Blender?
Yes, we are working with them.
Yeah.
In fact,
Okay.
we've been in contact several times. We are projecting in the list, and many of the members of the robotics team are aware of this project.
Okay. Because one of the key developers of the Blender game engine is Benoit. I don't know if Benoit is here.
Benoit will see.
Ah, there he is. Okay, so that's the guy you have to talk to.
Yes, in fact.
You already met. Okay.
Yes.
I wanted to connect some people. Okay. Questions?
Thank you. One of the questions I had is about you're basically using the game engine as a virtual environment, like
Yes.
like this is not real; it's a virtual setting. But the robots, of course, depend on all kinds of physical apparatus like actuators, servos, motors, gear belts, all those types of things. Are those simulated in the game engine, or do you use?
Yes, yes. That's the whole idea of MORSE, is to simulate all of that, all of the sensors. Of course, it depends on the degree of realism that we want to use, and in the intended use. We are not simulating the very low level, say, interaction between the wheels and the ground, or very low level tasks, because we are intending to use it for higher level reasoning for the robots. So we're not dealing with that kind of computation. We are using slightly more intelligent, slightly more simplified robots. Still, we emulate how a certain sensor may gather data and send it. But in general, we have motors for the robots with different kinds of input. So for instance, we may have a robot which receives speed information that it should give to the wheels. And well, the robot will try to move at certain speed and rotation, or we can just instruct the robot to go to a certain place. In that case, we forget about the speed, and it's a simulated robot that should be able to, by itself, get there.
I wanted to ask, does your robot learn? So do you have a learning system? So for example, you give a task, and the first time it runs into some problems, it has to find a very complicated way to reach where it wants to go. Next time, will it go the same way, or do you have a system, a learning system in?
Well, that's not.
And if you have that in Blender, of course.
No, that's not in Blender. All of that is done outside again.
This is not specifically Blender, but in which part do you generate signal noise?
In which
Because
part?
the data signals coming out from Blender, everything is perfect,
Yes,
but you have to simulate a camera on the on the other end, and the image is completely blurry, and the processor has to make sense of it. So in which part
right now
do you have the signal noise?
We can do that with, within Blender, let's say. We have the Blender will have the camera which captures an image and then stores it as a data structure. After that, we can apply the modifiers, which in this case, if we are using a modifier for that large amount of data, an image from the camera is the largest data we have, we can implement a modifier in C and call it as a module from Python. And we do that before sending the data to the client software. Otherwise, we could do that outside of MORSE, but in an intermediate step before actually giving the data to our clients, or have the client at the noise. But we have implemented already that kind of noise for cameras or for other sensors.
Okay, thank you. 1 or 2 minutes break, and then we go to the next talk about teaching mathematics on high schools.
Gilberto. No sabía dónde estabas ni quién eras.
Excuse me, I missed the beginning of the talk, but what is the platform inside the robot? Is the Python running inside the robot?
No, we have no. We can have both. Yes. No, not necessarily. No. The real robot is independent. It can run without Blender.
Yeah. So it has its own, let's say, its own machinery.
Yes. Yes, we
There's
have
no
the
interpreter.
interpreter in
In
the
the
robot.
robot. It's just
Yes. The robots have
so that's not Lex, a big software.
yes, the robot software.
I've worked once.
Let's try a little bit. This resolution. Let's try it. Let's try this one. So it's now extended on that one.
Where's
And if you want to check, so maybe you want to use that monitor as your primary one. In that case, can you try it for this one? Okay, so that's what I meant. So if we can you open the preference?
again?
And make it the principal. So when you
Okay.